Hello, and welcome back to Physics 41, University Physics 3. This is now the last lesson for the last chapter of this course. But before we proceed, I would like to emphasize some things that I forgot to mention in the previous lesson regarding resonance. So, one application of resonance, as I mentioned in the previous chapter, was the radio receiver technology. And what happens is when you tune your the LRC circuit, when you tune the frequency, the angular frequency of your LRC circuit to the angular frequency of the electromagnetic waves broadcasted by the radio station, then that is when resonance happens. So you have a very clear signal, or the very clear amplitude, current amplitude and voltage amplitude of the radio signal. Once you tune your radio station, or sorry, your radio to the frequency of the radio station. So that is all I'd like to emphasize. So for this last lesson, we need to review the concept of mutual inductance. So in your lesson on inductance, so if you have two coils with varying number of windings or turns, or number of coils, and current is flowing through, say, one coil, then it will actually induce a magnetic field on the second coil. And since a magnetic field is now induced in the second coil, there will now be a current flowing in the second coil. And since this current will also be changing, so this will also induce a current on the first coil. So hence the term mutual inductance. They induce a magnetic field on each other. And the induced EMF is related to the number of turns and the change in magnetic flux with respect to time. So for our last topic on transformers, this will actually use the concept of mutual inductance. So transformers are basically electrical devices used for stepping up or stepping down alternating current or alternating voltages. So it's made of two coils or two windings. You have a primary coil or primary winding and a secondary coil or the secondary windings. And these two coils have different number of turns. Say the turn for the primary is N1, the number of turns for the secondary is N2, and they are wound or wound in an iron, solid iron core, so that the magnetic field will just be confined in the iron core in this manner. So if there is an alternating voltage V1 in the primary coil, then a resulting secondary alternating voltage will be induced in the secondary coil. So depending on the number of turns, you can actually design your transformer to increase the voltage or to decrease the alternating voltage. So take note, there is no physical contact between the two coils, and the current is actually transferred from the primary coil to the secondary coil without physical contact. So that is what we call inductance. So unlike direct current actually needs actual physical contact. But for alternating current, you can actually transfer alternating current wirelessly from one coil to another coil. So that's one advantage of alternating current. So the ratio of the secondary to the primary voltage is given by the ratio of the number of turns. So if it is a step down transformer, meaning the secondary voltage is smaller or lower, then the ratio of N2 over N1 is less than 1. If it is a step up transformer, meaning the secondary voltage V2 is larger, then N2 over N1 is greater than 1. So in a transformer, the average power is actually conserved, meaning V1 I1 is just equal to V2 I2. So you can actually calculate the current changes or the transformed current from the primary to the secondary using this equation. So, okay, so very commonly sight outside your homes are these electrical posts with this large cylindrical can here, and this is actually our transformer. So in this case, this is a step-down transformer. So in the Philippines, you have high voltage, low current traveling along from the source to the transmission lines, and when it reaches this post, it steps down the voltage to 220 volts, but it steps up the current to actually 10 amperes. So 220 volts and a maximum of 10 amperes. So that's a step-down transformer. So in your charger adapter, in your cell phones, in your laptops, or any electronic device, you actually also have a step-down transformer. But aside from a transformer, it also rectifies the alternating current. When you say rectify, it actually converts the alternating current to direct current. So you have in a charger, you actually have a step-down transformer plus an AC to DC converter. So the reverse actually from DC to AC, that's what we call inverter. So this is converter from AC to DC. So it steps down. For example, cell phone charger, that's 5 volts. So it steps down the voltage from 220 volts to 5 volts and then converts the 5 volts AC into 5 volts DC. So those are examples of transformers. Okay. So I will just make this last lesson very short. So I'll just have one example. So this is an example of a step-up transformer. So in this example, a friend returns to the United States from the Philippines with a 960 watts coffee maker designed to operate from a 240 volts line. So usually in the Philippines, our power outlet can accommodate from 200 to 240 volts voltage VRMS. So she's from the Philippines. She bought a coffee maker designed for a 240 volts na line. So what can she do to operate it in the USA standard 120 volts? So the problem is like this. In the US, the outlet is actually 120 volts. So the device actually needs 240 volts. So you need a transformer. And the transformer is a step-up transformer. So you need to step up the 120 volts to 240 volts so that you can use the device on a 120 volt na outlet. So here, 120 volts, that's your V1. There will be a primary current I1 here. The transform voltage is V2, 240 volts, and there will be a secondary current I2. Okay. So what can she do to operate it at the USA standard 120 volts? So she needs a transformer. And how do you describe a transformer? By the number of turns. So V2 over V1 is just equal to N2 over N1. So V2 is 240, V1 is 120. Therefore, this ratio is actually equal to 2. So it's greater than 1, so it's a step-up transformer. So he needs a transformer wherein the ratio of the number of turns of the primary and the secondary coils N2 over N1 is equal to 2. That's what she needs. Okay, for letter B, what current will the coffee maker draw from the 120 volt na line? So from the 100, this is your coffee maker, your device, and it will actually draw two types of current. So first, the primary current, I1, and this will be transformed to the secondary current, I2. Okay. So let's first solve for the primary current. So these currents, by the way, these currents and voltage I1 and V1, these are RMS values. So in terms of RMS values, the average power is just V RMS I RMS. So therefore, the average power is just equal to V1 times I1. So therefore, I can solve for I1. It's actually the average power over V1. So the average power is given as 960 watts. This is the average power divided by V1. V1 is 120 volts. So 960 over 120, that will give you the primary current of 8 amperes. So to solve for the secondary current I2, you can actually use the same equation, average power over V2, or since the power is conserved, meaning V1 times I1 is just equal to V2 times I2, you can also solve it using that. So given I1, so it's just V1 over V2 times I1. And you will still get the same result. So power over V2, V1 over V2 times I1, you will still get the same result of 4 amperes. So this is the secondary current, 4 amperes. Okay. So lastly, what is the resistance of the coffee maker? So you already know the voltage. You already know the voltage VRMS supplied to your coffee maker is 240 volts. So you already know the current I2. Then you can solve for the resistance of this device. So it's just V2 over I2. And you will get 60 ohms. So V2 is 240 volts, I2 is 4 amperes. So you will get a resistance of 60 ohms. So as a summary of our results, the transformer needed must have a ratio of N2 over N1 equal to 2. So the primary current is 8 amperes, the secondary current is 4 amperes, and the resistance of our coffee maker is 60 ohms. And so that's it for this lesson or this chapter. And basically, that's also it for this course. So I hope you have learned something about electricity and magnetism as we have progressed through this course. And I hope you good luck in your exam. So I hope you all pass the course. So thank you for listening to our videos and good luck.